Hello, good morning. Today we shall discuss some problems on set theory, also some objective questions which can help you to solve the more problem. First, distributive properties. Distributive properties. A bit intersection is distributive over union. Intersection is distributive over union means A intersection B union C equals to A intersection B union A intersection C. A intersection B union C equals to A intersection B union A intersection C. Second bit, A union B intersection C equals to A union B intersection A union C. How we can prove these two results? We shall prove by using set algebra, not by particular examples. In previous classes, in 10 classes, you have proved this by taking particular examples. But here we shall prove by set algebra. Means how we can prove this? Let us see. First A bit, similarly way you can prove B bit. Two set A and B are said to be equal if A subset B and B subset of A. Then we say that A equals to B. Whenever two sets are equal, if A equals to B means A is a subset of B, B is also subset of A, then in that case we say that A equals to B. First we have to prove A intersection B union C is a subset of this set, and similarly we have to prove this set is also subset of this set. Then we conclude that A intersection B union C equals to this set. First take arbitrary element X belongs to A intersection B union C. Take an arbitrary element X. You cannot prove by particular cases. You have to prove in general cases. In set algebra, first take an arbitrary element from this left hand side or right hand side, whatever you may be, you choose. First let X belongs to A intersection B union C. We have to prove this X is an element of this set. That means every element of this set is an element of this set. Means A intersection B union C will be subset of this set. In similar method, we can also prove that this set is also subset of this set. Then we can conclude that A intersection B union C equals to A intersection B union A intersection C. Then implies X belongs to A. For intersection we use word and X belongs to B union C. If X belongs to A intersection B, we write as X belongs to A and X belongs to B. In the same argument, if X belongs to A intersection B union C, then X belongs to A and X belongs to B union C. For intersection, we use the word and. This implies X belongs to A and X belongs to B or X belongs to C. For union, we know that if X belongs to A union B, we write as X belongs to A or X belongs to B. For the same argument, we write X belongs to B union C means X belongs to B or X belongs to C. Then we use the distributive properties. X belongs to A and X belongs to B. Or x belongs to A and x belongs to C. As we know that suppose A into B plus C, we write as A into B plus A into C. Similarly, x belongs to A and x belongs to B. 1. Here the middle word is OR, so here the middle word is also OR. X belongs to A and x belongs to C. This line is important. This implies x belongs to A intersection B or x belongs to A intersection C. For x belongs to A and x belongs to B, we write as x belongs to A intersection B. X belongs to A and x belongs to C, we write as x belongs to A intersection C. Now, this can be written as x belongs to A intersection B union A intersection C. We have take x belongs to A intersection B union C. Now, x is an element of A intersection B union A intersection C. Means every element of this set is an element of this set. That means A intersection B union C is subset of this set. That is our argument. First, we have to prove this is subset of this set and this is also subset of this set. Then we can conclude that A intersection B union C equals to this set. अतएव A intersection B union C is subset of A intersection B union A intersection C. This is first. We take x is an element from this set and we prove that this x is also element of this set. Means every element of this set is an element of this set. That means A intersection B union C is the subset of A intersection B union A intersection C. That is first case. Again, we have to take x from this set and we have to prove this x is also element of this set. Take x belongs to A intersection B union A intersection C. This implies x belongs to A intersection B or x belongs to A intersection C. For union we write OR. This implies x belongs to A and x belongs to B, one bracket, or x belongs to A and x belongs to C. Now, x belongs to A, x belongs to A, we write as once x belongs to A and x belongs to B or x belongs to C. This implies x belongs to A and x belongs to B union C. Instead of x belongs to B or x belongs to C, we write as x belongs to B union C. That means x belongs to A intersection B union C. First, we take x as an element of this set. Now we have proved that x is also an element of A intersection B union C. अतएव A intersection B union A intersection C is subset of A intersection B union C. This is 2. From 1 and 2, we conclude that A intersection B union C equals to A intersection B union A intersection C. Means intersection is distributive over union. That is the process. That is known as the process of algebra. In this way we have to prove. In particular cases you cannot prove. You have to take x is an arbitrary element and first you show that this set is subset of this set. Again this set is also subset of this set. Then we can conclude that this set is equal to this set. Another method you can also adopt, that is if you put double implication here, then at the same time you can say that A intersection B union A intersection C is a subset of A intersection B union C. That is 2. अतएव A intersection B union C equals to A intersection B union A intersection C. You can also use the double implication. Instead of 2 part of proof, you can convert to single part if you can put double implication. In this way, you try for the second bit yourself, that is distributive properties. Some problem you have to solve by method of algebra. Next, A difference B union C equals to A difference B intersection A difference C. First bit. Second bit, A difference B intersection C equals to A difference B union A difference C. We have to prove these two results. This is also called as De Morgan's law also. Another form of the De Morgan's law. Proof A. It means similar method. We have to prove this set is subset of this set. Again this set is also subset of this set. Then these two sets are equal. This is the method to prove the two equal set. Let X belongs to A intersection B union C. First you have to take X is an arbitrary element from this set. This implies X belongs to A and X does not belongs to B union C, because we know that if X belongs to A difference B, we write X belongs to A and X does not belongs to B. In the same argument, we write as if X belongs to A difference B union C, then X belongs to A and X does not belongs to B union C. If X belongs to A and X does not belongs to B and X does not belongs to C, here you have to prove and, here you have to put and, because we know that if X belongs to B union C, we write X belongs to B or X belongs to C. If X does not belongs to B union C, then its negation will be becomes X belongs to B and X does not belongs to C. This is the argument. If it belongs to, then you have to write or. If it does not belongs to, then you write instead of union you write and. X does not belongs to B and X does not belongs to C. Then use the distributive properties. X belongs to A and X does not belongs to B. 1 and X belongs to A and X does not belongs to C. Since here is and, you have to write here also and. In between B and C, which word is written here, you have to put here. If it is or, then you write here or. If it is and, you write here and. And you connect A with B and A with C after the X belongs to A with this connecting, that is and. If it is or, then we have to connect A with B with or A with C with or. Since it is and, we have to connect A with B with and, A with C with and. This implies X belongs to A difference B and here we have to write X belongs to A difference C. This implies X belongs to A difference B intersection A difference C. Now here X is an element of this set, means this set is subset of this set. If we use double implication, then we can write A difference B union C is subset of A difference B intersection A difference C, and A difference B intersection A difference C is a subset of A difference B union C. Means this set is subset of this set, again this set is also subset of this set, hence both are equal. A difference B union C equals to A difference B intersection A difference C. In the same method you can prove second bit, that is De Morgan's law. This is also another form of the De Morgan's law. You go through books and see more examples and prove some questions like this, and also discuss some objective questions which can help you better preparations. De Morgan's law. First bit, A union B A union B whole dash equals to A dash union A dash intersection B dash, A intersection B whole dash A dash union B dash. Same method. With the help of set algebra, we have to prove these two results. First, prove A bit. In similar manner, you can prove B bit. Let X belongs to A union B whole dash. This implies X does not belongs to A union B, because we know that if X belongs to A dash, we write as X does not belongs to A. So if X belongs to A union B whole dash, we write X does not belongs to A union B. This implies X does not belongs to A. Instead of union, we write AND, because here does not belongs to. If it is belongs to, then we have to write OR. If it does not belongs to, we write AND, because the negation of OR is AND and negation of AND is OR. X does not belongs to A and X does not belongs to B. This implies X belongs to A dash and X belongs to B dash. This implies X belongs to A dash intersection B dash. Now we take X is an element from this set, and we prove that X is also element of this set, means this set is subset of this set. And if we use double implication, then A dash intersection B dash is subset of A union B whole dash, and A union B whole dash subset of A dash intersection B dash. A union B whole dash equals to A dash intersection B dash. In the same manner, you can prove second bit. This is known as De Morgan's law. You have to prove some results like that. A intersection B delta C equals to A intersection B delta A intersection C. This is symmetry difference. This symbol is used for symmetric difference. Previous classes we have already discussed this. Know that symmetric difference. What do you mean by symmetric difference? We have already discussed. Similar way, let X belongs to A intersection B delta C. This implies x belongs to A and x belongs to B delta C. Since it is intersection, we use the word AND. This implies x belongs to A and x belongs to B difference C, or x belongs to C difference B. Why? Now we know that if x belongs to A delta B, we write x belongs to A difference B, or x belongs to B difference A. So for A delta B, we write x belongs to A delta difference B, or x belongs to B difference A. This implies x belongs to A and x belongs to B difference C, or x belongs to A and x belongs to C difference B. We connect A with this set and also A with this set, and we use OR here and connect with AND. Now x belongs to A and x belongs to B and x does not belongs to C. For x belongs to A difference B, B difference C, we write x belongs to B and x does not belongs to C. Here x belongs to A and x belongs to C and x does not belongs to B. For this part we use. Now x belongs to A and x belongs to B, we write as x belongs to A intersection B. X belongs to A and x belongs to B. Instead of that, we write x belongs to A intersection B. And x does not belongs to C. We can argument that if x does not belongs to C, then x cannot be an element also A intersection C. If an element x is not in C, so it cannot be an element of A intersection C. Which one is the element of A intersection C? Which is both in A and also in C? Since it is not in C, so it cannot be an element of A intersection C. So if x does not belongs to C, we can argue that x does not belongs to A intersection C. My argument is that if x is not an element of C, it cannot be an element of A intersection C. X is an element of A intersection C when x is an element of both A and C. Since it is not an element of C, so it cannot be an element of A intersection C. Similarly, here we write x belongs to A intersection C. Instead of x belongs to A and x belongs to C, we write x belongs to A intersection C. And here x does not belongs to B. We can argue that x does not belongs to A intersection B because x is an element of A intersection B when x is both element of A and B. Since it is not element in B, so it cannot be an element of A intersection B. That is an argument. Now for this we can write x belongs to A intersection B difference A intersection C, because x is an element of A intersection B but not an element of A intersection C. That means x is an element of A intersection B difference A intersection C. Or x belongs to here A intersection C difference A intersection B. Suppose this is x and this is y. So x is an element of x difference y, or here x is an element of y difference x. Take it as x and this is y. So this is x difference y or this is y difference x. Means x belongs to x delta y. For this way we can write we can write x belongs to A intersection B delta A intersection C. X belongs to this difference, this union A intersection C difference A intersection B. If it is X, it is Y. This is X difference Y, this is Y difference X. Here it is OR. So that is the A intersection B delta A intersection C. We know that X belongs to A delta B. That means X belongs to A difference B or X belongs to B difference A. So in the same argument we use this. Take it as X and it is Y. X difference Y or Y difference X means X delta Y. Use double implication here. Then you can write A intersection B delta C equals to A intersection B delta A intersection C. This way we can prove other problems in the same argument with the help of set algebra. Another problem, A difference union I from 1 to n Bi equals to intersection I from 1 to n A difference Bi. How we can prove this? In the same way, take X belongs to A difference union I from 1 to n Bi. Previous class we have discussed I from 1 to n union I from 1 to n Bi means B1 union B2 union dot dot union Bn. For this union of n set we use this symbol. This implies X belongs to A and X does not belongs to union I from 1 to n Bi. Same argument, A difference B means X is an element of A and X is not an element of B. This implies X belongs to A and X does not belongs to B1 union B2 union Bn. Union I from 1 to n Bi we write as B1 union B2 union dot dot union Bn. This implies X belongs to A and X does not belongs to B1 and X does not belongs to B2, and since it does not belongs to, so we write n instead of or dot 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 and X does not belongs to Bn. Now each B1 B2 will be connected with A. X belongs to A and X does not belongs to B1 and X belongs to A and X does not belongs to B2 and dot 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 and X belongs to A and X does not belongs to Bn. Each set A is combined with B1, A with B2, A with B3, A with Bn. Now we can write X belongs to A difference B1 and X belongs to A difference B2 and dot 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 and X belongs to A difference Bn. Now we can write as X belongs to A difference B1 intersection A difference B2 intersection dot dot intersection A difference Bn. Now this can write as X belongs I from 1 to n A difference Bi. First use the suffix 1, then we will get A difference B1. If U is 2, then it is A difference B2. If it is N, then A difference Bn. And in each set, there is a middle term, that is intersection. Now we use double implication so that we conclude A difference union I from 1 to n Bi equals to intersection I from 1 to n A difference Bi. So this is a method to prove the equality of sets. Many problems, if you go through books, then you will solve problems easily. Especially go through more objective questions which will help you better way. If A equals to A dash, then E equals to phi. If and only A equals to A dash, if and only E equals to phi or U equals to phi, universal set. There is two part, necessary part, sufficient part. If we use, suppose A is equal to A dash, then we have to prove U equals to phi. If you suppose U is equal to phi, then you have to prove A equals to A dash. Suppose U equals to, suppose A equals to A dash. We have to prove U equals to phi. Let X belongs to U. This implies X belongs to A union A dash. We know that A union A dash is equal to U. So instead of U, we write as A union A dash. This implies X belongs to A union A. We know that A dash is here A. This implies X belongs to A. This implies X belongs to A intersection A. We know that A is equals to A intersection A by idempotent law. This implies X belongs to A intersection A dash because A equals to A dash. We can use A is A dash because we suppose that A equals to A dash. This implies X belongs to phi because we know that A intersection A dash is equal to phi. We have taken that X is an element of U, but X belongs to phi. That means U is a subset of phi. But we know that phi is a subset of every set. Phi is also subset of U. This implies U equals to phi. This is one part. If you take U A equals to A dash, you have proved that U equals to phi. Suppose U equals to phi, then we have to prove A equals to A dash. U means A union A dash. A union A dash equals to phi. When union of two set is phi, then both set are phi. Union of two set phi means both set are phi. That is A equals to phi and A dash is also equal to phi. This implies A equals to A dash. So this is two part. One is necessary part, another is sufficient part. First we take A equals to A dash. We have proved U equals to phi. Second, we take U equals to phi and we have proved that A equals to A dash. If A union B equals to A intersection B, then A equals to B. If A union B equals to A intersection B, then A equals to B. How we can prove this? If A union B equals to A intersection B, we have to prove A equals to B. prove. Let X is an element of A. We have to prove A equals to B. That means we have to prove A is a subset of B, B is also a subset of A. Then we can conclude that A equals to B. Take X is an element of A. Then we can say that X is also element of A union B. This implies X belongs to A intersection B. Since A union B equals to A intersection B, so instead of A union B, we can write as A intersection B. This implies X belongs to B because A intersection B is a subset of B. Each element of A intersection B is also in B. So X is also in B. Now we have take X is an element of A, but here X is an element of B, means A is a subset of B. That is one part. Similarly, let X belongs to B. This implies X belongs to A union B. Here we cannot use double implication because if X is an element of A intersection B, it is necessary that X belongs to B. But converse is not true. If X is an element of B, it may or may not belongs to A intersection B. So in this case, we cannot use double implication. So we have to prove by two parts. This implies X belongs to A intersection B. This implies X belongs to A because A intersection B is also subset of A. Here we take X is an element of B and we got X is an element of A. That means B is a subset of A. Hence A equals to B. So very simple and easy result. If A union B equals to A intersection B, we conclude that A equals to B. But we have to prove in this process, in an algebraic process, not in particular examples. As many as problem you can solve, then your fundamental will be clear. So go through books and solve more problems, that will clear your idea. A intersection A union B equals to A. How we can prove? A intersection A union B equals to A. Take X is an element of A intersection A union B. This implies X belongs to A and X belongs to A union B. Because here is the symbol is intersection and we use word and. This implies X belongs to A and X belongs to A or X belongs to B. Now we have to use the distributive properties. X belongs to A and X belongs to A. 1. Here we have to use or X belongs to A and X belongs to B. Now for this we can write X belongs to A intersection A or X belongs to A intersection B. This implies X belongs to A or X belongs to A because A intersection B is a subset of A. So for X belongs to A intersection B, we write X belongs to A. This implies X belongs to A union A. This implies X belongs to A. That is A intersection A union B subset of A. But here also we cannot use double implication because if X is an element of A intersection B, then X is an element of A. But if X is an element of A, it may or may not true that X belongs to A intersection B. So we cannot use double implication. But it is obvious that but it is obviously A is a subset of A intersection B union A. Hence A intersection A union B equals to A. Similar way, you have to prove some more problems. Another important result you have to remember that cardinality of A union B equals to cardinality of A plus cardinality of B minus A intersection B cardinality. We can prove this, but you have to use this formula to solve the problems. How we can prove? This is set A and this is set B. This is A difference B and this is B difference A, and this part is A intersection B. Now A difference B, B difference A and A intersection B are three disjoint sets. These three are three disjoint sets because they have no common element. Again, A difference B union B difference A union A intersection B equals to A union B, and union of these three sets equals to A union B. That means cardinality of A union B equals to cardinality of A difference B plus cardinality of B difference A plus cardinality of A intersection B. This take as 1. But we know that cardinality of A difference B is same as cardinality of A minus cardinality of A intersection B. We know that cardinality of A difference B is cardinality of A minus cardinality of A intersection B. And also cardinality of B difference is cardinality of B minus cardinality of A intersection B. Now we substitute these two results in equation 1. That is cardinality of A union B equals to cardinality of A minus cardinality of A intersection B plus cardinality of B minus cardinality of A intersection B plus cardinality of A intersection B. Now 1 is cancelled with this. Now remaining terms are cardinality of A plus cardinality of B minus cardinality of A intersection B. You can use this formula to solve many language problems which are also given in your textbook. Similarly, for three sets we use the formula cardinality of A union B union C as cardinality of B A plus cardinality of B plus cardinality of C minus cardinality of A intersection B minus cardinality of B intersection C minus cardinality of C intersection A plus cardinality of A intersection B intersection C. You can use this formula to solve many problems which are given in your textbook. So, if any problems, then we shall discuss in further classes. Thank you. Go through your books, solve more problems, more objective problems. Whenever the class will open, we can discuss and interact with each other. So, keep it and prepare yourself in your home and take it as tasks and complete as soon as possible. Again, thank you all.